Okay, so we have two more talks in this session. The first one is on practical settlement bounds for longest chain consensus, and Peter is going to give the talk.
Hi, everyone. I'm Petar Gazi, and I would like to talk to you about the speed of longest chain consensus today. And this is joint work with Lindgren and Alex Russell. So when I say longest chain consensus, what I mean is this class of protocols for maintaining a distributed ledger where parties collect transactions into blocks, and then they put them into this ever-growing block tree that is connected by hash links. And the right to create these blocks and append them to this block tree is distributed or is decided based on some leadership lottery. We consider both proof of work and proof of stake leadership lotteries in this work. Importantly, honest leaders are mandated in this whole class of protocols to extend the longest chain in this block tree that they see. Whereas the adversary, of course, when he's allowed to create a block, he can put his block wherever he wants. Parties interpret the longest chain that they see as consisting of two parts: the stable ledger state, in which they believe all the transactions in this part, this is a prefix of the longest chain, all the transactions in this part are there to stay forever, and some unstable suffix that might potentially change in the future due to the longest chain rule. And this already illustrates that the settlement in this class of protocols is both gradual, in the sense that the more blocks are amassed on top of a block of interest with some transaction that I care about, the more certain I can be that this transaction stays in the ledger forever. And it is also subjective, because the protocol itself does not prescribe where this threshold should be, and it is up to the user interpreting the ledger to decide which blocks are considered stable and which transactions should be considered stable. And this already illustrates that arguably the most important question about this class of protocols from the user perspective is, how long should I wait? So if there is a transaction in the longest chain that I see, well, how many blocks should I see on top of the block carrying this transaction to rely on this transaction, that this transaction will remain in the ledger forever, except with some acceptable error probability. And this is exactly the problem that we look at in this paper. So we provide a rigorous method for obtaining settlement guarantees for both proof of work and proof of stake longest chain consensus, under the assumption of a particular honest and adversarial power, be it hashing power in proof of work or stake in proof of stake protocols, and under the assumption of some bound on message propagation delays. And beyond that, we also, to illustrate the practicality of the bounds, we put them to work to obtain some concrete numerical results of practical interest, both from our proof of work and proof of stake. So this is what we do, and now I will try to illustrate how we do it. And for most of the time, I will talk about the proof of work case, because that one is easier. And only towards the end of my talk, I will sketch the differences to the proof of stake setting. So the model that we work in is one where we divide time into discrete slots of a particular length, and we assume that all messages are delivered within delta slots, for some constant delta. And this model is natural for proof of stake, where the protocols typically impose this slot structure on the timeline by themselves. Whereas it is also a good approximation for proof of work when we let the length of the slot go towards zero. We model the leadership lottery as independent Poisson processes with two rates, RH and RA, for honest and adversarial block creation, respectively. And this seems to be exactly the right model for proof of work, and it's also a good approximation for proof of stake. And finally, we consider adversaries that can execute an arbitrary strategy to break settlement, as long as they do not break the hash function that keeps the hash tree together, and they cannot break the lottery mechanism that distributes the right to create new blocks. I will now introduce you to tools that we use to describe an execution of such a protocol. These are characteristic strings and block trees. So a characteristic string is simply a string where each symbol of this string corresponds to one slot of the execution. And the symbol contains both the number of honest and adversarial lottery successes in that slot. And you can see an example in this slide. And given such a string that describes the outcomes of the lottery, you can describe one execution of the protocol by a tree, just like the one I show you in the slides, which basically captures all the chains that were created in this execution of the protocol that is compatible with the string that describes the outcomes of the lottery. And for such a tree to be valid, to describe a valid execution, it needs to satisfy a set of properties. And one that I would in particular want to bring to your attention is one that I call the honest depth property in this talk, which is that each honest block in this tree needs to be deeper than all honest blocks that were created at least delta slots ago. And this is something that just follows from the description of the protocol, because if honest parties create a block, then they propagate it immediately. Then due to the network assumption, we have a guarantee that this block will be received by all honest parties within delta. And then the honest parties are mandated to create new blocks on top of the deepest block they see. So, and this together already implies the property that I show you here, and that we will refer to later. So to be able to argue about settlement, we need to be able to answer the following question. So does a string, such a string as here, describing the outcomes of the lottery, admit a block tree with long diverging segments? Because such long diverging segments basically prevent settlement, because it's not clear which of the chains is going to be the actual ledger in the end. Let's look at some examples. This is a tree in a benign scenario where all the lottery successes were honest, but it illustrates that even in this case, there might some forking might occur. Here, the creator of this honest block created a fork simply because he was not aware of this honest block due to network delays. And of course, the situation is much more complicated once adversary enters the picture, at least for two reasons. So first of all, the adversary doesn't need to respect the honest depth rule that I told you about. He can put his blocks whenever he wants. And second of all, he doesn't need to propagate his blocks immediately and universally. So he can try to do all kinds of things with his blocks. And here you can see a situation where these two properties allow the adversary to create two long diverging segments for a lottery outcome described by this string. So to be able to answer the question that I asked, which is given such a characteristic string, does it or does not allow an execution that leads to such deep forks? We use an analytic quantity called margin that I will introduce next, and I will start by illustrating it in an example. So consider this tree, and consider a particular slot of interest, for example, because it contains a block in which there is a transaction we care about. So what interesting can be said about this tree? Well, the upper chain might be held by some honest party as being the longest chain at the moment that it has seen so far, and that's simply because this honest party might not have yet seen these two blocks due to network delay. At the same time, the lower chain is one block longer. And so if this chain is served to this honest party, the party will switch to this chain and will change its mind about how the ledger looks up to this slot L. And this intuition is exactly what the notion of margin is trying to capture. So margin is the maximum length advantage of a chain that differs from some honest view at slot L. So again, looking at this picture, this might be an honest view. This is a chain that differs from the honest view before or up to this slot L, and its length advantage is 1 because it's one block longer. And for that reason, the margin of this particular tree is a positive one, it's +1. And we also generalize this notion to the whole strings by saying that the margin of a string is simply the maximum margin over all compatible forks describing executions. And the crucial property of margin, why it is useful for this analysis, is that if margin of a characteristic string is negative, then after an execution that is described by this string, the honest parties chains will agree up to the relevant slot L. And the reason is exactly following the same intuition. If margin is negative, it means that the adversary doesn't have any chain up his sleeve that would be competitive to or longer than the chains that the honest parties are holding. And so he cannot make them change their mind about how the ledger looks up to this slot L. So this is the intuition behind margin. And taking this one step further, if we know that margin with respect to slot L becomes negative in some slot L plus T, and then remains negative forever, we know that in this slot T, the ledger up to slot L is settled and will never change. Let me now make a small detour and tell you about the related but easier problem that was previously answered. Anyway, let me tell you about an easier but related question that was already answered in previous work, which is for what parameters of honest and adversarial power and network delays do the protocols from this class of longest chain consensus even provide eventual consistency. So asking just the asymptotic property that eventually you do get consistency without caring about any particular concrete bounds. And this has been answered already in previous work, which actually in 2 concurrent works at CCS 20, where it was shown that both proof of work and proof of stake longest chain consensus is secure in this sense if the adversarial power is upper bounded by this term depending on the honest power and the network delays. And interestingly, this is tight because if the adversarial power exceeds this term, then actually the simplest attack you can think of, the private chain attack, will break the protocol. And so I would not like to show you as a starting point for our work. I would like to show you how one can derive this consistency region argument using the margin quantity that I told you about. So let's think about the spectrum of all values that the margin quantity can take. These are all integers, and let's split it into 3 regions. The so-called cold region, where margin is sufficiently negative so that the adversary is significantly lagging behind honest parties, intuitively speaking. Then we consider a hot region, which is the opposite, where the adversary is significantly ahead of the honest parties. This corresponds to high values of margin. And then we have a critical region where margin is close to 0. And this corresponds to situations where the adversary is somehow in a close race, intuitively speaking, with the honest parties. And this is the situation that will turn out to be most difficult to analyze. And one can show, and this previous work has shown, that if margin is in this happens to be in this hot region, then with further execution of the protocol, with every adversarial success in the lottery, margin gets increased by 1, whereas with it gets decreased by 1 with every honest success that happens at least delta slots after the previous such honest success that was counted for this purpose. And exactly the same behavior occurs also in the cold region. And notice that under the assumption of this inequality that I showed you that is necessary and sufficient for security, both of these behaviors will result into a negatively biased random walk performed by the margin quantity as we sample new and new lottery outcomes. And this, together with a simple observation about the critical region, where one can observe a very low yet still constant probability descent event that makes the margin descent from the critical region to the cold region. This is already sufficient to describe the dynamics, the asymptotic dynamics at least, of the margin quantity. and show that it escapes to -infinity at the linear rate. Let me remind you that once margin becomes negative and remains negative, it means that the honest parties won't disagree up to slot L, and so we have settlement up to this particular slot L. And the relevant thing about this argument for us is that it depends mostly on the bias that the random walk exhibits outside of the critical region. And this previous work has a very wide critical region, and arguably a very loose analysis of the probability of crossing it, which is sufficient for the asymptotic statement, but this kills all chances of getting good concrete bounds for settlement of this class of protocols. And this is where our work enters the picture. So what we do in this paper is that we provide a novel way to analyze the execution of a protocol from this class in larger chunks that we call phases, and that I will talk about in a minute. And this allows for obtaining a similar analysis, but with a much narrower critical region. And it allows for a practically tight analysis of margin while crossing this critical region, which together with the bias that we understand already in the other two regions results into margin recurrences or a recurrent description of margin that can be simulated for practical settlement bounds. So let me quickly talk about that. So how does this phase-based view look? So these phases, these are just consecutive non-overlapping slot sequences, where the goal when defining a phase is to have the following property, that if any if honest parties create any blocks during a particular phase, then any honest party creating a block in the subsequent phase must be aware of all blocks that were created by honest parties in the previous phase. And the way we achieve it is we simply define a phase to be any interval that ends with a delta long period of honest silence, meaning no honest blocks were created. And notice that this is sufficient for the property I told you about, because if, say, any honest blocks are created in the green phase, they must have been created prior to this silence period. And so during the silence period, they will be delivered to all honest parties, and so the honest parties are aware of them when creating blocks in the blue phase. And having this phase-based view in mind, our goal for the analysis is to devise recurrences that upper bound margin, let's say, looking at this picture after the blue phase that is depicted here, based on two inputs. The first one is the margin prior to the blue phase, so that would be the margin after processing all the previous phases, and then some properties of the blue phase itself. So the recurrences would be of this form, and these then allow us to iteratively upper bound margin throughout the full execution in a phase-by-phase manner. So we do devise such recurrences for proof of work. I will now give you some intuition about how they look. The ideal recurrence that one would hope for has the following form. So we would like to see that the margin after, again, here's the same picture as before, that the margin after processing the blue phase would be equal to the margin prior to the blue phase, plus some term that describes some contributions by the adversary, namely increasing the margin by 1 for each adversarial success in the lottery during the blue phase, and minus, so decreasing the margin for some contribution that plays in favor of the honest parties. And so what is this term? This H delta function is simply the minimum honest depth that honest blocks must take, the honest blocks that were created based on the lottery outcomes, if only they want to obey the honest depth property that I told you about at the beginning. So there is some mandated minimum depth at which honest players must play their blocks or put their blocks, and this H function describes exactly this depth for for this phase in question. And so with every increase of this depth, margin actually decreases by 1, as can be seen from the recurrence. And so this is the ideal recurrence we would hope for. And we show that this indeed exactly applies both in the hot and the cold region. But more importantly, we show that the critical region is as narrow as possible, meaning if this ideal recurrence does not bring margin to hit or cross 0, then margin behaves exactly according to this recurrence. And it is only if this recurrence would make it cross or touch the value 0, where a different loser description needs to come into play. We also provide such description for the critical region. We give 2 upper bounds for margin depending on depending on whether margin is positive or negative prior to the blue phase. And in both of these, the intuition is that some of the honest contributions are given up upon. So these are non-tight upper bounds for the critical region. And finally, we also have observed a rule that allows margin to cross 0. So if it is margin is 0 and a particular favorable event occurs, then margin becomes -1. So these are the recurrences for describing margin in a POW longest chain protocol execution. And these are the recurrences that we simulate to get our concrete settlement bounds. And we also devise similar recurrences for proof of stake. Unfortunately, I won't have the time to go over those, but let me just quickly describe the differences. They begin pretty early because already the notion of a tree is different for proof of stake. Mostly, or one significant reason for that is that in proof of stake, a party can create many blocks if it wins the lottery, as long as each of these blocks extends a different chain. This is somehow a property of proof of stake. Then also the analysis is more complicated because, in fact, we need 2 intertwined characteristic quantities to describe the execution. There is a quantity that is called reach. I won't go into the details of it, but it's somewhat simpler to understand than margin. But then there is a proof of stake version of margin that is defined in the same way or very similar analogous way as the proof of work margin. However, its analysis is more difficult because in the proof of stake case, it depends on the previous quantity on the reach. And so all the recurrences that we obtain, they need to compute these 2 quantities in tandem. And this is what the recurrences that we obtain for proof of stake also do. So we do get such recurrences for proof of stake. And I can quickly compare them to their proof of work analogs. So the proof of work recurrences are simpler, but both can be numerically simulated. That's what we do to get our explicit results that I show you in a minute. And it turns out that the proof of work recurrences actually witness slightly faster settlement, which I will also illustrate in a minute. And so theoretically, these recurrences are the main result of our work on the theory side. And then we also put them to work. So I would just leave you with a few results that come out of these for settings of interest. So we obtain results for both proof of work. As an example, we use the parameterization of Ethereum prior to their switch to proof of stake. As you can see, our bounds improve on the state of the art, on prior state of the art. But perhaps more importantly, we also provide first such explicit and practical bounds for longest chain proof of stake. And in particular, in the paper, we give an example for the Cardano parameterization. And these are practically tight, as you can see that our bounds for settlement violation probability after 20 blocks is clearly at most 3 blocks from optimum, given the lower bounds that come from a simple attack. And finally, this also allows us to compare the settlement guarantees provided by proof of work and proof of stake longest chain paradigms in a quantitative way for the first time. So that would be it. Thank you, and I'll be happy to take questions.
Thank you. We have time for one quick question. Yeah, actually, I have a quick question. So your analysis, right, applies to existing proofs of work and proofs of stake mostly. But if you were to like build a protocol from scratch, like with like all of this analysis like built in, do you think you can get something better? Like it seems that seems almost sure, right? I mean,
well, so yes, this is an analysis for a class of protocols that follow the longest chain rule paradigm, right? There are other paradigms too.
right, but I mean, okay, so the numbers that you gave are for existing protocols that weren't designed to follow your analysis. So my question is like, if you like build a protocol from scratch with like the tools that you present here in mind, can you get something that has even better conversions rate? Or
Yes, so the input to the analysis are these three quantities: the honest adversarial power and the network delays. Well, the machinery can be executed for any such triple. And of course, then you can ask what could be the optimal parameterizations. But of course, those depend on these inputs. In particular, you need to make some assumptions about against what fraction of the adversary you want to be resilient, and what do you think are the delays in your network. But if you make such assumptions, then you might be able to optimize the parameters of this class indeed, and this might give you a well-founded approach to parameterize such protocols, and that's actually something we are looking into.
okay. Thank you very much. Let's thank the speaker again.
Can you hear me?
Yes.
Perfect.
He can't see you though. Okay, so the next and final talk of the session is about completeness theorems for adaptively secure broadcast, and Ran Cohen is going to give the talk.
Okay, thanks a lot, Julian. And this is a joint work with Juan and Vasilis. And I know that we're in the consensus session, but I want to start to talk about MPC. So MPC, we have a set of parties that they run a protocol, and they want to compute something in a secure way, even when some of them are corrupted. And by security, we normally compare the computation to an ideal model, where we have a trusted party that helps the parties carry out the computation. And we have an adversary that can also corrupt some of the parties, but is very restricted. And we say that a protocol is secure if for every real-world adversary, we have an ideal model adversary that can carry out the same attack. And this is a very strong definition, very nice. And one of the nice things about it is that it's very flexible. So if we want to consider adaptive corruptions, where the adversary can corrupt parties during the protocol based on stuff that he sees, then we can simply modulo technicalities, adjust the definition, and say that for every adaptive real-world adversary, we have an adaptive ideal world adversary. Right? So the adversary can see something that happens and then decide who to corrupt. So we also allow the ideal world adversary to corrupt at the same time. And then the protocol proceeds, and then the adversary corrupts another party. So we also allow the ideal world adversary to corrupt that other party, and then the protocol completes, and we want that to say that no distinguisher or no environment can tell real or ideal apart. Now, there are many good things about this definition, right? It's a holistic definition. It gives us all of the security requirements we want in one shot. It gives us composition. It depends on the technicalities we use in the definition. Then we get different types of composition guarantees. We have a very clear notion of security that we achieve, right? Everything is captured within this ideal functionality, within the trusted party. But one can always say that it's also harder to prove. To prove a simulation-based security normally can be a tedious task, especially when we talk about adaptive corruptions. And maybe it's an overkill. Right? Maybe we get too strong of security than what we actually need. So that's a fair question. And we can also think of a weaker notion of security for MPC, right? A property-based definition. So we want that the protocol will satisfy a list of properties versus some adversary, adversary from some class. So either information theoretic or computational, but we want those set of properties. Now, when we talk about such definitions, how do we capture adaptive corruptions? Is it fair to say that we want those set of properties to be satisfied facing an adaptive adversary? But if we have a protocol that satisfies those properties against an adaptive adversary, can we say that the protocol is adaptively secure? Okay, think about it. This is kind of the meta question that we look at in this work. And as a case study, we focused on adaptively secure broadcast. So in a broadcast protocol, the goal is to emulate a broadcast channel. What's a broadcast channel? Here's a broadcast channel. I talk, everybody hear me, right? And everyone hears what I say. So we want to actually capture that property. And with the broadcast protocols, as the previous talk said, we want normally two properties. We want that all parties will terminate with a common output. And if the sender is honest, we want them to terminate with the sender's input. Now, should a protocol that satisfies those properties facing an adaptive adversary be considered an adaptively secure broadcast protocol? If you'll think about it, I hope that the answer that you'll get is no. Right? We don't want this exact set of properties. We don't care about parties that were honest at the beginning. Right? We only care about parties that are honest at the end. If a party is getting corrupted, then it can output whatever it wants. It shouldn't harm the agreement that we want. Also with validity, we only care about validity when the sender is honest at the end. If you think about a protocol like Dolev-Strong, if the sender begins as an honest party, but is getting corrupted along the way, it can inject a different signature that will force the parties to output a different value than what he had at the beginning. So if we adjust the properties like that, now a protocol that satisfies those set of properties against an adaptive adversary, is it considered as an adaptively secure broadcast protocol? Maybe. Maybe yes, maybe no. I think now it's kind of depending on the setting. And let's illustrate a setting where this might be problematic. So let's say we have a set of parties, and each party broadcasts a bit. And the adversary's goal is to make the set of bits be as close as possible to the all zero string. Let's say we want to agree on which movie we want to see. 1 is an action movie, 0 is a drama movie, and the adversary kind of wants to push us towards drama movies. So this is kind of the honest setting. Each one broadcasts a bit. And now what happens when we have a static adversary? So the static adversary doesn't see the parties in, but he can guess which parties will broadcast 1. So let's say he has 3 corruptions, he guesses 3 corruptions, sees what they have, and then if he guesses the party that has input 1, it can make it send 0. Right? So he can succeed with some probability, depending on number of parties and the distribution of the inputs. What happens if we have adaptive adversary, but we use a broadcast channel? Right? So let's say everyone in his turn comes on stage and then says their choice. Right? Before someone talks, the adversary has no idea what he's going to say. When I'm standing here, even I don't always know what I'm going to say next. So the adversary can only know what I'm saying when I say it. In that case, the adversary has the power that he can see what happened so far before deciding whether to corrupt the party or not, but he doesn't know the party's actual input. So he can kind of guess like before in some sense. And and so on. So it can, roughly with every party has a 50-50 probability of guessing correctly. What happens when we use a broadcast protocol instead of a broadcast channel? So most broadcast protocols in the literature follow this paradigm. We start with the sender that sends its input to everyone. And then the parties want to reach agreement on what they saw. And such protocols normally achieve agreement and validity, even facing adaptive adversaries. But when we look at adaptive corruptions, there can be other attacks that are not captured within those properties. For example, let's say that by chance, the first party to receive the message is a corrupted party. So it gets the first message, X, the sender's input, and then decide, do I like X? If so, I will let the protocol continue. If not, the adversary can corrupt the sender and send a different value, or simply crash the sender if it's a failed stop adversary. So in that case, the adversary has more capabilities. It has a double dipping advantage. It can be the first to learn the input. I think of a Russian adversary. We assume normally that corrupted parties get it first, but if not, maybe it's simply lucky. So it gets to see the input value of the sender, and then decide whether it wants to corrupt the sender and change the output of the honest parties. So this is a double dipping attack that we don't normally have when I go on stage and talk. So should we be worried? That seems like a very strong adversarial capabilities. The adversary within a communication round can first see the message, then go corrupt the sender and change the rest of the messages. So that's very strong assumption. And indeed, if we assume some stronger communication assumption, where all of the communication that party sends is done in an atomic fashion, we can bypass this impossibility. We need to adjust the protocols. Like the left strong won't be secure even if we have this strong communication assumption, but we can get around it. But should we be worried? It turns out that in many blockchain settings, for example, we use a diffusion network to propagate the message. And in that case, we cannot really have an atomic multi-send capability. And then such attacks can be really painful. So what can we do? So in this standard broadcast protocols, if you use them to kind of solve the previous question, the adversary can first see the input bit of every party and then decide whether it wants to corrupt them or not. So here, input 1, so it'll corrupt the party. The second one is input 0, so we won't corrupt it, and so on. And you can see which parties have input 1 and choose those parties to corrupt and to adjust their input values. And looking back, this is not really the security notion that we get from a broadcast channel with adaptive corruptions. So there is a gap. And Hirt and Zik has actually studied this gap. And they focused on a simulation-based definition for broadcast. So they defined the megaphone functionality, kind of a broadcast channel that, as we described it before. Here, the sender sends the input, and everybody gets it together. The adversary can always corrupt the sender and decide what the input is going to be, but he won't do it based on the actual value that is being broadcasted. They also defined a weaker broadcast functionality. They called it unfair broadcast. Here, the sender sends the input to the functionality. The functionality gives the input to the adversary, and the adversary can now decide whether he wants to corrupt the sender and change the input value. And later on, all of the other parties will get whatever was sent. And they showed here Tenzikas that this is kind of the ideal functionality that is being realized by most of the broadcast protocols in the literature. And we can get it for any number of options if we have a PKI. On the other hand, the stronger functionality, even with a PKI, we can only get it as long as we don't have a dishonest majority. Once there's a dishonest majority, there's an impossibility. They proved a very nice impossibility, showing that no broadcast protocol will be able to realize the megaphone functionality. And this is a very annoying impossibility, right? We don't really like such an impossibility. So we can try to think whether we can somehow relax the setting to bypass it. And simulation-based security really gives us very strong guarantees, right? It gives us composition, so it requires more than maybe what we need. As we said, maybe it's an overkill. What if we, and some of the protocols in the literature kind of focused on property-based definition with this intuition in mind. But indeed, maybe if we use a property-based definition, we can bypass this impossibility. So that's a fair question. Also, it's an adaptive adversary. We know that if we use a programmable random oracle, we can also bypass all kinds of impossibilities. So if we use a random oracle model, can we bypass this impossibility? Another thing is that in this impossibility, the adversary gets to see the message and then operate. What if we hide the content of the message and reveal it to the adversary at a later point in time, where it's already too late for him to corrupt the sender? This is what a time lock puzzle gives us. So if we have time lock puzzles, can we bypass this impossibility? So all of those are good questions, and we kind of try to address them in this work. So what do we show? First, we show that this impossibility is not something that is coming from the simulation-based paradigm. It's something much deeper, something inherent when we talk about adaptively secure broadcast, even with the property-based definition. To argue that, we had to come up with some property that captures this attack. So we discussed a new property that we believe is important in certain settings when we use a broadcast protocol. We call it corruption fairness. And then we show a full characterization of the feasibility of adaptively secure broadcast, given both in the property and the simulation-based definitions. So here Zika showed that we cannot get simulation-based definition. We showed that the property-based definition can also not be captured, at least in a large class of protocols. This class captures all of the existing protocols we have in the literature so far. And we showed that also random oracle won't help in achieving it. If we have a time lock puzzle, interestingly, we can get the property-based definition, but we cannot not get the simulation-based one. And if we have both a time lock puzzle and a programmable random oracle, we can get a simulation-based adaptively secure broadcast. Now, along the way, we also prove something that I find very interesting, a composition theorem that captures objects that deal with resource-restricted adversaries, like a time lock puzzle. And we captured that in the complexity-based definition of time lock puzzles. So that's something very subtle and interesting. How much time do I have? Okay, so the plan now is kind of to gloss over the ideas of the proofs without any technical detail. So I try to bypass, to kind of put all of the technicalities under the rug. So what is this new property of corruption fairness? Very informally, it says that the adversary shouldn't be able to first see the input value of the sender and then corrupt the sender and change the honest parties as a function of it. More formally, we kind of capture it in a game. So we have a challenger and an adversary. The challenger chooses a random bit and runs the broadcast protocols towards the adversary. The adversary can adaptively corrupt parties and play with the challenger. At the end, the adversary wins if A, the input bit is 0 and the sender remained honest, or B, if the input bit is 1 and all of the honest parties output 0. So one way to do it is to corrupt the sender and change its input. And we said that protocol satisfies this property if for any adversary, the success probability is roughly 1/2. And this is now a definition of a property-based definition of adaptively secure broadcast. Satisfy agreement, validity, and also corruption fairness. And we show that if we have a protocol that, as a sanity check, if we have a protocol realizing the megaphone functionality, it will also satisfy the property-based definition. So how do we show the impossibility of the property-based definition? We define a class of protocols where we have a specific round R star and a specific set C star of size n/2 - 1. And we want the following two properties to hold. First, up until round R star, no minorities of the parties actually have the information to know what X is. Roughly speaking, if everyone else crashes, they will have an error, a noticeable error in guessing what the input is. And at round R star, we have a set C star that knows what the output, what the sender's input is. So given their joint view, we can know what the input is with overwhelming probability. Now, all of the existing protocols in the literature actually fall within this class, where R star is even the first round, right? Before the sender talks, no one knows anything. And in the first round, people know what the sender's bit is. But and we can also extend the class to other capture mode protocols, but I don't think it's that interesting. Now, given that a protocol within that class, the adversary can now corrupt the set C star, wait until round R star, the sender sends all of its messages to that set, and now the adversary can know what the sender's input is going to be. If it's 0, it will let the protocol resume. And if it's 1, it will corrupt the sender and crash it. So if the input is 0, then there's a tiny negligible probability that the adversary will make a mistake and corrupt the sender. And if the input is 1, then there's a noticeable probability that everyone will output 0. So that violates the property that we want. Can we overcome this impossibility? So what we want effectively is that at round R star, the set C star will have all the information to compute the sender's input, but it will not be able to do it before the next round begins. And that's exactly the property we get from a time lock puzzle. Time lock puzzle allows the sender to kind of put its input in some puzzle, and if people work hard enough, they'll get the output. If they don't work hard enough, they won't learn any. So we also need to consider a more restricted set of adversaries here. But we want that within, we said that an adversary is R, T bounded. If within our communication rounds, the adversary can compute only circuits of depth at most T. And given that, we now have a very simple protocol to realize broadcast, the property-based definition, where the sender puts its bits in a time lock puzzle, sends the puzzle to everyone, and the adversary has the time to corrupt the sender given the puzzle, but it doesn't know what's inside it. So we have this fairness property, and now everyone gets the puzzle and they can work hard and solve and extract the bit. So that's nice. But is this protocol simulation-based secure? That's tricky because a time lock puzzle is a committing object. So when we simulate, the simulator has to commit to some puzzle and send and show it to the environment or distinguisher. But it doesn't necessarily know what the sender's input is. In that case, if the simulator kind of asks the megaphone functionality to get the sender's bit, the sender bit gets locked, and the simulator won't be able to change it. And now, if the adversary wants to corrupt the sender and change the sender's input, the simulator gets stuck. If the sender doesn't ask the megaphone functionality for the bit, then it can guess what the bit is going to be, and then it will make an error with probability 1/2 if the adversary doesn't corrupt the sender and let the protocol continue and resume properly. And we use this intuition to kind of leverage a broader impossibility to show that even with time lock puzzles, we cannot get the simulation-based definition of broadcast in the dishonest majority setting. Can we overcome this impossibility? So now we want to make the time lock puzzle non-committing in some sense. And so we want to allow the simulator to simulate a puzzle and then choose what's going to be inside it. Can we make a time lock puzzle non-committing? With magics, right? In the programmable random oracle model. Here we use a standard trick where we don't put the message in the time lock puzzle, but we put some random seed. And then we hash the seed and have a one-time pad with a message, and that allows the simulator to equivocate the content later on. So in the programmable random oracle, we can get simulation-based adaptively secure broadcast. Now, one last thing I want to say in this talk is caution. Because look at the protocols, both protocols that we have. We have a simulation, we have a trusted party that has the broadcast, runs the broadcast for us. If we replace this trusted party, say with Olevstrom, everything's going to be okay. We won't hit any barrier, right? So the sender sends the input, the time lock puzzle to everyone, and then they reach agreement and solve it. But what if we adjust the Olevstrom to a slightly different protocol? So in this protocol, at a certain point, we have some party PI that sends the time lock puzzle to party PJ. Party PJ solves the puzzle and returns the bit to party P1. Other than that, we run the Olevstrom as usual. In that case, this is a broadcast protocol. It has the corruption unfair security that we need here, but the party, it's secure against PPT adversaries. There is no restriction on the computing power, the sequential power of the adversary and of the corrupted part, of the honest parties, sorry. In that case, when we compose, if we take this protocol to realize the broadcast functionality we had before, then first, the sender sends a time lock puzzle to PI. PI now can send this puzzle to PJ, and PJ will solve the puzzle for PI and gives it the input. Now, the sender knows what the input is, and he can corrupt the sender if he wants or not. And the reason this is tricky is because normally we restrict the capabilities of the adversary when we consider security of protocols. But here, the adversary can use resources of honest parties. So we have to restrict also the resources of honest parties when we talk about composition. And that's very subtle. We do, however, prove a composition theorem, the first composition theorem in that setting, that is very limited and restricted and is enough for what we do. I think it's a beautiful question to extend it. That's something we are working on now. So to summarize, be aware when we talk about adaptive security that a set of properties doesn't always capture everything that we want. A simulation-based definition is really holistic in that sense. It gives us properties that we don't always know that we need. So I vote for simulation-based security, but this is the characterization we have, and that's it for now. So thanks a lot.
Thank you for the talk. So we have time for maybe 1 or 2 questions, then the session is over.
So when you talk about limiting the computational power of honest parties, is it sort of just an artifact of the proofs and in terms of composing protocols together, or would you get into a situation where, for example, a company upgrades their data center and all of a sudden now their protocol is insecure because their computational power is suddenly sort of doubled, for example?
That's a good question. It's kind of unclear yet, exactly, at least to me, it's unclear yet what are the compositional guarantees we get when we talk about resource-restricted settings. So I think it's a wonderful question. I can't give you an answer for that one yet.
Can you help me understand? So would PKI plus erasures be an option to avoid the impossibility?
No, the impossibility also holds with erasures.
And so
Yes.
what's the obvious problem with just letting the sender kind of?
You mean the simulation-based one?
No. So what would be the issue with a strawman proposal where the sender signs the message he wants to send and then erases the key before sending it?
You mean if we do the left song?
Then it seems like it cannot be corrupted based on the message.
Yeah. So if we have the atomic multisend, then we know that we can get it. We have to, if we adjust the left song, then we can get it.
Okay.
The left song as is doesn't. Maybe with erasure it does, but
Okay.
could be. I didn't check, but it's possible. But we can get the simulation-based definition if we have a stronger communication assumption. If we don't have the stronger communication assumption, then we can simply crash the sender. And then parties won't get it in. It's not about signing a different message necessarily.
Okay.
Okay, thanks.
Actually, I have a follow-up question on that question.
Mhm.
So when you're saying like adaptive, sorry, the multicast model that you mentioned, right? So which version are you referring to? So there is like a version where the adversary can take back messages that were sent by previously honest parties. So it can adaptively corrupt them, take back the message. But it's commonly conflated with a model where you can't interrupt a sender that wants to send to all parties at once. So which aspect of that model do you actually need?
So
get,
we
like,
don't, to get around this impossibility, we don't need to retract messages that were sent.
So you only need to interrupt a sender.
Yeah, we need to make sure
Okay.
that when a sender starts sending its message to someone,
Yeah.
it will complete the sending to all of the recipients and will not get corrupted until all of them got the message.
Okay, thanks. Thank you. So thanks, speaker again.